In our earlier lectures, we have discussed about the integral control, how the integral control acts on the error, how it eliminates offset, and how it is a very useful part of the PID control. In this particular lecture, we will be discussing about one of the major issues of the integral control, which is known as the integral windup or reset windup. We'll be also discussing about the solution to this problem, and we will be understanding the reset windup with the help of animation and practical examples. So let's start with it. So what is integral control? So we know that integral control or reset action that acts on the error as long as the error is not zero. This is the property of integral action, and this helps to eliminate the error. But on the other hand, if the error could not be eliminated totally, then as the error is non-zero, the integral action continue to act upon it. And if the time interval is long enough, larger and larger values of manipulated variable gets generated due to the reset action, leading to complete opening or closure of the valve. This particular situation is known as integral windup or reset windup. We can also call this situation as the saturation of the controller because we cannot go further beyond to this point. Now, if we want to understand through our mathematical equation, so here is it. So we know that integral action output is shown as gain multiplied by the reset gain into the integral of error. Now, as long as error not equal to 0, the integral action will continue to act upon it, and this will lead the output to either upper limit or lower limit. And in this way, integral or reset action got wind up. Now, what are the solution to it? There are many solutions. I have identified the three major solutions that are used in the industry, and we will understand this solution, one of the solution, with the help of a practical example. So one solution could be initializing the controller integral to a desired value, for instance, to the value before the problem. Another way is to use conditional integration, that is disabling the integral function until the to be controlled process variable has entered the controllable region. And third is zeroing the integral value every time the error is equal to or crosses the zero. Don't worry about the solution if you are not understanding it properly through these lines. We'll explain you with the help of an example. Now, Now, in this particular slide, we will understand how uh, the reset or integral windup happens and how the anti-reset really works. Now, in the y-axis, on the upper portion, we have taken PV and SB, and the lower portion, we are taking MB. Now, suppose uh, the operation was going on at a 60 degree centigrade temperature. Maybe suppose this is the process can be a simple heat exchanger where the hot and cold fluid are getting mixed, right? And our aim is to control the outlet temperature. So just we can draw somewhere here. So maybe there is one line which is hot and there is another line that is cold, right? And these two are getting mixed and this is the outlet. So our aim is to control the outlet, and this outlet temperature is the PV. Okay, and there is a valve at the inlet in the cold line inlet. Okay, so by allowing more fluid through the cold line, the temperature is controlled. Okay, now suppose in the beginning the temperature is set at 60 degrees centigrade, and output is at 12%. Okay, and this is maintaining the PV at 60 degrees centigrade. Now there is a operator suddenly increased. Now just 1 minute, let's erase the our drawing first. Now operator suddenly increase the set point from 60 degree to 90 degrees centigrade. This will result in decrease in the MV value, right? MV value will start decreasing from 12%, and the temperature start rising. So as the set point as fixed is 90 degree, the temperature will try to match 90 degree, but this is a too high a set point which cannot be achieved in this process. So eventually, after reaching a temperature of around 75 degree, the temperature cannot increase further more. And in this time, the valve has also slowly closed to 0%. That is completely closed. It cannot go beyond this value. Now, as long as error is there, the integral action will keep on acting on it, and this will cause MV value to be more and more negative side, right? But practically negative MV is not possible, so it will take the MV value to 0. Now then operator understands that he had done a mistake and again reduces the set point value from 90 degree to 60 degree. Now as it happens, the controller should act immediately, but as it has been driven to 0% because the continuous integral action, it cannot act immediately. It has to nullify the integral action that has gone into other direction. So there is a delay in action, but ultimately it acts and takes down the temperature value from 75 degree to 60 degrees centigrade. And then again, as there is no error, there is no integral action, and MV value remains constant. So as you can see here, there is a delayed response from the controller due to the windup. The controller is supposed to be acting at this point the when the set point has been changed, but it has taken this much additional time to act. Sometimes this is very critical for the process. That's why reset windup is always present in modern controllers. So now we take the situation when reset windup is present. What will happen in that situation? So now if operator increases the set point to 90 degree, Again, the controller will try to match the set point, but it will not be able to because it is a too high a set point. Process variable will also go to a certain value and then it will remain at that point, right? So as there is an error, integral action will be present there. But again, when the operator understands that he has made a mistake and reduces the set point to the original value of 60°, integral action immediately start responding because anti-reset windup is present in this case, and it will try to reduce the temperature PV value immediately to the set point. So as you can see, in this case there will be, as the value has increased suddenly and to much higher level, there will be an undershoot of the temperature, but it will be stabilized slowly. But at least there is an immediate response from the controller whenever there is a change in the set point. And this is the feature of the controller with wind-up protection. So on the left side without wind-up protection, and on the right side with wind-up protection. So hope you have understood from this the difference between these two situations. Now, as I promised at the beginning of the video, so let's take another practical example of the wind-up situation. Suppose there is a vessel and our purpose is to control the level of this vessel to a particular point. There is a feed-in line that is going inside it, and there is a control valve here, and the flow is going out from the feed out line. Okay, and this control valve, and the upstream of the control valve there is a pump. Okay, so through the pump water or any liquid is going through the control valve and entering into the vessel, right? So there is a LT here, level transmitter, and that sends signal to a level controller, and level controller sends signal to the control valve to regulate its flow so that the level of the vessel can be maintained. So suppose at a certain point of time, and the level controller employs PI control. Okay, now suppose that we are maintaining the level at 50%. Okay, and the process is going on, everything is smooth. Now all of a sudden this pump got tripped. Okay, so when the pump got tripped, suppose this valve is open at 50%, level is also maintained at 50%. Now at the pump got tripped, there is no feed into this vessel, but feed out is still going on, right? Feed out is still going on. Now what will happen? Level will come down, right? Level will come down from 50% to say some other percent, say 48% or 40%. Now our set point is not changed. Set point is still 50%. So our set point or SB is 50%. Our PV is at 40%. So there is a error, right? There is an error of 10%, and which is non-zero. So as there is a non-zero error, the I action will continue to act on it. Okay, the I will be acting on it, on this valve, because the error is still there, right? So what will happen? It will it will add more and more manipulated variable, increase the manipulated variable. So the valve opening will increase from 50 to 60%. Suppose for 10 minutes it increased to 50 to 60%. And the pump has, in the meantime, the pump has got a serious problem, and it will take, suppose, for 1 hour to rectify it. So in the 1 hour, the error is still there, and it will cause the MP to increase continuously, and it will cause the output of the controller to increase, say, 100%. So the valve will open at 100%. So valve will remain open at 100%. So now what is the problem? So this is the situation, this is the reset wind up situation or integral wind up situation. Okay. So what is the issue with it? Yes, the valve is opening 100%, but what is the issue with it? Suppose after 1 hour, the pump gets rectified, okay, and the pump starts again. Pump again starts, starts giving the flow. So what will happen? As the valve is open 100%, so much flow will come altogether, right? And it may happen that due to the high opening of the valve, so much flow will go into the vessel and the vessel will overflow. So this is a dangerous situation, right? Because overflow is always considered as bad and dangerous, and if it is not water, some other hydrocarbon, it will may lead to fire and other accidents, right? So that's why we need to have some anti-reset wind-up or anti-wind-up feature inbuilt in the controller or the system. So one of the easiest way to tackle in this particular scenario is to take input from the pump running. Maybe pump running feedback may go into the controller. And whenever the pump is tripped, right, it will not allow the integral action to increase further, or it can stop its MB value to be fixed at that value it last got, right? So suppose the at a certain point of time MB value is 50%, and at that point of time pump has tripped, so it will not allow MB value to increase more than 50%. It will hold the MB to 50%. So in this way, when the pump again starts, it gets the same situation when where it left off, right? And there is no chance of overflow or any other hazard. So this is uh, anti-reset or anti-wind up basically, and there are many ways to implement this. uh, Digital controllers now come with this feature inbuilt. It was a major problem when there was analog controller earlier, and but now with the digital controller it comes with lots of feature, and anti reset or anti wind up is one of the common feature which is present on all digital controller. Still we need to configure it well, and we need to see that we have not bypassed this particular feature. So hope you have understood what is integral or reset wind up and how to control it. Thank you.